All right, so last time we started a new module. We started a new section on open channel flow. We talked about why you need to know about open channel flow in civil engineering. We talked about the places that you will encounter open channel flow as a civil engineer. So just to refresh my memory here, what were some areas where you will encounter open channel flow as a working civil engineer? What are kind of the most common applications? Stormwater, so very good. So that's probably the place where most of you will encounter open channel flow. So when you're designing things like gutters, storm drains, channels for conveying water at the side of roads, so ditches, as well as larger water infrastructure as well. So rivers themselves, impoundments, dams, that sort of thing. All of that will require a knowledge of open channel flow. So that's what we're going to be covering from now up until the end of the course. We talked about the differences between pipe flow and open channel flow. So to help refresh my memory, what were some of the major differences between pipe flow and open channel flow that I mentioned last time? So thinking about how we analyze these problems. So first of all, the things that are the same, they obey the same basic physical dynamics. So they obey conservation of mass. They obey Newton's second law. That applies for both pipe flow and open channel flow. What were some of the differences between pipe flow and open channel flow that we need to account for? Yes. Very good. So for open channel flow, the channel geometry, so I'll say for open channel flow, the cross-sectional geometry is not constant. So when we were talking about pipes, we could always assume that the cross-sectional area of flow was equal to the cross-sectional area of the pipe because that pipe is known to be flowing full. With open channel flow, that's not the case. And our cross-sectional area and thus the hydraulic geometries that we're interested in will change as a function of the depth of the water. So that's one of the major differences we're going to have to account for. What was another major difference in terms of how we looked at the force balance? Force balance. Yes.
The conservation of mass and momentum is the same.
Conservation of mass and momentum is the same. So that is true. Remember, though, that the pressure term, we treated it a bit differently for open channel flow as opposed to pipe flow. So if you'll remember, for our, I'll say pressure is treated differently. So you'll remember our energy equation for pressurized pipe flow was something like this: P1 over gamma plus Z1 plus U1 squared over 2G is equal to P2 over gamma plus Z2 plus U2 squared over 2G plus any head losses from 1 to 2. How does this energy equation change for the case of open channel flow? Right. So instead of looking at the pressure head, we'll typically be concerned with the depth of flow in an open channel, given the relationship between the hydrostatic pressure and the depth. So you'll remember the pressure in a water column is equal to the specific weight of water times the depth. Thus, these pressure head terms here, P1 over gamma and P2 over gamma, we treat these as just the depth of the water at points 1 and 2, respectively. So from now on, instead of looking at that pressure head term, we're going to be using the depth of the water to essentially represent that pressure head. So those were the two main differences that I talked about last time. Differences that you'll want to keep in mind between pressurized flow and open channel flow. We talked about different types of open channel flow. So uniform, rapidly varying, gradually varying, unsteady, steady. So starting off this module, I want to first talk about uniform flow in particular. So this is a case that you will encounter very frequently, probably the most common case, especially if you're designing urban drainage infrastructure. So who remembers what characterizes uniform flow? So what condition characterizes uniform flow? Why is it uniform? Yes. Yes, very good. So the water depth, velocity, and discharge are constant throughout the length of the channel. At any given time. So this is probably the simplest case to look at. It's also the most common case used in design. So what I want to do next is I want to take a closer look at uniform flow. I want to look specifically at the force balance, and I want to show another way of characterizing uniform flow in terms of the forces, and also derive our fundamental equation for analyzing uniform flow, the Manning's equation, as you'll see it applied to open channel problems. Right, so let's first take a look at uniform flow. We're going to take a look at a control volume. So we have our channel bottom. And we have our water surface. And for the case of uniform flow, we know that the depth has to be the same at all points in the channel. So we can see that the depth at the upstream end is going to be exactly the same as the depth at the downstream end. As a consequence of this, the water surface for uniform flow will always be parallel to the bottom of the channel because the depth remains constant throughout the length of the channel. So we have that our depth is constant. We also have that our discharge is constant. So Q1 and Q2 are the same. And our velocity is also the same at all points in the channel. So U1 is equal to U2. So let's just write that out explicitly. We have that H1 is equal to H2, Q1 is equal to Q2, and U1 is equal to U2. So this is from the definition of uniform flow. All of these quantities have to be equal for the case of uniform flow. This will not always be the case, but for uniform flow, all of these quantities will be constant throughout the channel. So let's take a closer look at a control volume of water within this channel. And let's take a look at the forces acting on that control volume. Okay, so we have our control volume here. What are the forces that are acting on the water in this control volume? Gravity, very good. So we will have a gravitational force pointing down. And the component of that gravitational force in the longitudinal direction will be equal to, so if the gravitational force we call Fg, the component in the longitudinal direction will be Fg times the bottom slope, approximately equal to it. Okay, what other forces do we have? There's two more. Hydrostatic, so there will be a hydrostatic force acting on the sides of this control volume. And let's call this FP1 for the hydrostatic force at the upstream end, FP2 for the hydrostatic force at the downstream end. And the last force is friction. So that will be acting at the bottom of the channel. So we have a frictional force acting opposite to the direction of the flow, which I'll call F sub F. So if we apply a force balance to this control volume, let me write it up here. We have that the sum of forces is equal to the time rate of change of momentum. We arrive at our momentum equation. So that, as before, is given by d cubed by dt plus d qu by dx plus the acceleration due to gravity times the cross-sectional area times quantity dh dx. So remember, we showed that last time. The gradient in the pressure is now represented by the gradient in the water depth, i.e. the slope of the water surface, minus the bottom slope plus the friction slope is equal to 0. So that's our general momentum equation. This works for any flow condition. Let's take a look and see how this simplifies under the case of uniform flow. So I'm going to rewrite this entire equation. Put this up here. Oops. So we have dq by dt. And I'm going to take this term here and I'm going to break it down using the product rule. So this term here becomes u times dq dx plus q times du dx. So this is just from the product rule from calculus. Okay, to this, we're going to add our forces. So that's going to be g times a times quantity dh dx minus the bottom slope plus the friction slope is equal to 0. Okay, so first of all, for uniform flow, we're always talking about steady state conditions. So this first term here, the time varying term, this is 0. Uniform conditions apply only for the steady state case. Okay, what other terms can we simplify here? So first of all, what about this term here? It's 0. Why is this 0? Right, Q is not changing with respect to X. We have that the flow, the discharge is the same throughout the entire length of the channel. So this is also 0. What about this term here? Is U changing throughout the channel? No. So this also is removed. And this term here that represents the hydrostatic force, we know that H is also not changing throughout the length of the channel. That's equivalent to saying that the hydrostatic force on the upstream side is equal to the hydrostatic force on the downstream side. So this term also becomes 0. So what we end up with is the following. I'm just going to write it here. Unfortunately, don't have a lot of space, but for uniform flow conditions, this entire momentum equation boils down to S naught is equal to SF. What does this mean? What is S naught? Bottom slope. What is SF? Friction slope. So the bottom slope is equal to the friction slope. What does this mean in terms of the forces? The bottom slope is equal to the friction slope. What does that mean in terms of the force balance? Which force does this bottom slope represent? Gravity. Which force does this friction slope represent? Friction. So what does this statement here imply about the forces? Sorry? Right. So this implies that the gravitational force is exactly balanced by the friction force. So let's write that down. We have that the gravitational force is exactly balanced by the frictional force. And that is another equivalent way of characterizing uniform flow. It's the condition where the gravitational force is exactly balanced by the frictional force, or equivalently, that the head loss is exactly equal to the change in elevation from one point in the channel to the next. So let's take a closer look at this formulation and see if we can derive an expression for working with uniform flow. So we have our fundamental condition for uniform flow is given by S naught is equal to SF. In other words, the bottom slope is equal to the friction slope. So remember that, keep that in mind. And from previously in class, we also have another expression for the friction slope. So remember that this is the energy loss per unit length. And we have an expression for the friction slope. It's given by the mean shear stress times the wetted perimeter times the length of our control volume divided by the acceleration due to gravity times the cross-sectional area times the density of water times the length of the control volume. Note that this is equivalent to the frictional force per unit weight of water. It's also equal to the energy loss or the head loss per unit length. So let's cancel out these delta X terms here. And notice that we have this term here, P over A. So what's another way that we can express P over A? Remember that A divided by P, the cross-sectional area divided by the wetted perimeter, is equal to what? It's equal to the hydraulic radius. So the hydraulic radius is defined as the cross-sectional area divided by the wetted perimeter. So P over A is 1 over R. So let's go ahead and rewrite our expression for the friction slope. So the friction slope is equal to the mean shear stress divided by G times rho times the hydraulic radius. And we can rearrange this for the mean shear stress. So this is equal to the acceleration due to gravity times the density times the hydraulic radius times the friction slope. So if you remember back to when we first started looking at equations for frictional losses, we derived the Darcy-Weisbach equation by taking this expression for the mean shear stress and equating it to another expression for the mean shear stress given by Newton's drag law. So let's go ahead and do that again. So from Newton's drag law, we have that the mean shear stress is equal to some drag coefficient CF times the density of the fluid times U squared over 2. So if we take these two equations for tau and equate them, we end up with the following. We have that the acceleration due to gravity times the density of the fluid times the hydraulic radius times the friction slope is equal to Newton's drag coefficient times the density times U squared over 2. And you'll remember that we could rearrange this expression for the velocity. So we get an expression for the velocity. It will be equal to the square root of 2g divided by this drag coefficient times the square root of the hydraulic radius times the friction slope. And you'll remember we took basically this whole term here, and we just called this some coefficient c, which we refer to as the Chasey coefficient. And all of the different friction formulations we looked at, whether it was Hazen-Williams or Darcy-Weisbach or Manning's equation, were just different ways of specifying this C coefficient. So let's write down our general form for this equation. So this is the Chasey equation. We have that the velocity of flow is equal to some coefficient c times the square root of the hydraulic radius times the friction slope. So as I mentioned, all of the different friction formulations we looked at were just different ways of specifying this c coefficient. Let's take a look at the Manning equation in particular. So the Manning equation comes from applying a particular form to this C coefficient. Basically, Robert Manning did a bunch of empirical studies back in the 19th century, fitting stage versus discharge data. And the coefficient that tended to perform well was given by C equal to phi over n, as in November, times the hydraulic radius to the 1/6 power. So remember this phi coefficient here, this is a coefficient that depends on your unit system. This r is the hydraulic radius. And what is this n term here? Manning's number that characterizes pipe material, more specifically roughness. Very good. So this is the Manning's roughness coefficient. So if we take this expression for C and plug it into our Chasey equation, we end up with what is usually called Manning's equation, sometimes the Chasey-Manning equation. So we're taking this expression for C, substituting it into the Chasey equation. What we'll end up with is U, the velocity of flow, is equal to phi over n, as in November, times r, the hydraulic radius, to the 2/3 power, times the friction slope to the 1/2 power. Usually, we'll see Manning's equation expressed in terms of discharge instead of velocity. So we can take this entire expression here and multiply by the cross-sectional area. To get the discharge. So the discharge given by Manning's equation is phi over n times the cross-sectional area times the hydraulic radius to the 2/3 power times the friction slope to the 1/2 power. So we've looked at this equation before for pipe flow. How can we simplify this equation further for the case of uniform flow? simplify it in terms of quantities we may be able to know or measure. So yeah, let's take a look at what quantities we might know. So let's say we're trying to predict the discharge. We know that this phi coefficient, this is either going to be 1 or 1.49, depending on our units. The roughness we can estimate from the material of the channel. The cross-sectional area we can measure. Hydraulic radius we can measure. Friction slope, well, what's a way that we can specify this friction slope? Yes. So for uniform flow, what is SF equal to? The bottom slope. Very good. So we can take this expression for Manning's equation and rewrite it for uniform flow. This becomes discharge is equal to phi divided by n times the cross-sectional area times the hydraulic radius to the 2/3 power times the bottom slope to the 1/2 power. So this gives us a way of predicting the discharge in an open channel just from the geometric parameters, so the geometry of flow, the slope of the channel, and information about the roughness of the channel. So this comes from the fact that for uniform flow, the friction slope is equal to the bottom slope. And this is the typical form of Manning's equation that you will encounter in open channel flow design. So note that this phi coefficient, again, this depends on your unit system. So phi is equal to 1 for SI units, and it is equal to 1.49 for US units. Now, it's important to remember that the Manning's equation is not dimensionally consistent. So these coefficient values are only applicable for discharge and your dimensions in certain units. So for US units, your geometric dimensions always need to be in units of feet, and your discharge will always be in units of cubic feet per second. For SI units, your geometric units will be in dimensions of meters. Your discharge will always be in units of cubic meters per second. So you can't use things like dimensions in inches when using Manning's equation. You have to use either feet or meters, and your discharge will either be in cubic feet per second or cubic meters per second. Okay, are there any questions on Manning's equation? We're going to be using this pretty extensively for the next couple of weeks. So I'm going to clear up any questions now. All right, let's take a look at an example. I'll do an easy example first. We'll move to a slightly more challenging example, and then I'll give you an even more challenging example after that. Okay, so let's say we have an 8-foot wide rectangular channel. With a bottom slope of 0.000, that's 3 zeros, 0.0004. And this is specified in something like feet per feet. It has a depth of flow of 2 feet. So I'll say the depth of flow is 2 feet. We're going to assume a roughness. So assume a Manning's roughness of n as in November is equal to 0.015. So this would be characteristic of something like concrete. And I want to determine the discharge assuming uniform flow conditions. So let's just draw out our channel. It's a rectangular channel. The bottom width is 8 feet. And the depth of water in the channel is 2 feet. So we can compute the discharge using the Manning's equation that we just derived. So recall Manning's equation is given by Q, the discharge is equal to phi over N as in November, times A, the cross-sectional area, times R, the hydraulic radius to the 2/3 power, times the square root of the bottom slope. So let's expand these terms for the different hydraulic geometry parameters. So A, the cross-sectional area, what is this equal to? What is A, the cross-sectional area, equal to? Right, it'll be equal to the bottom width times the depth of water. So this will be B times H. So sorry, I should write this. This is 8 feet. This is equal to the bottom width B. H is equal to 2 feet. So we have that the cross-sectional area is equal to the base, the bottom width times the depth. The hydraulic radius is given by the cross-sectional area divided by the wetted parameter. So this will be B times H divided by, what's our expression for the wetted parameter? Right, it'll be B plus 2 times H. So that would be 12, yes. So it'll be B plus 2H. We're going to raise this entire thing to the 2/3 power. Then we're going to multiply by the square root of our bottom slope. Okay, let's put in actual numbers here. So what is phi going to be equal to? 1.49 because we're in US units. N is going to be 0.015. B is 8, H is 2, so this will be 8 times 2. Again, in the numerator here, we're going to have 8 times 2. And then in the denominator, we're going to have 8 plus 2 times 2, all raised to the 2/3 power, times the square root of 0.0004. And if we evaluate this expression, what we'll end up with is about 38.5 cubic feet per second. So that is how we can compute the discharge given the depth, the hydraulic geometry, and the bottom slope of a channel. Let's do a slightly more complicated example. First of all, are there any questions on that application? No? Okay. Let's move on to a slightly more complicated example. So for the channel described in the previous problem, I want to determine the depth of flow if the discharge is 100 cubic feet per second. So our approach will basically start out the same. We'll have, from Manning's equation, Q, the discharge, is going to be equal to phi divided by N times A, the cross-sectional area, times R to the 2/3 times the bottom slope to the 1/2 power. For For this case, sometimes it's easier to expand this hydraulic radius term. So remember, hydraulic radius is A divided by P. So this becomes phi divided by N times A times A to the 2/3 divided by P to the 2/3 times the bottom slope to the 1/2 power. What will A times A to the 2/3 simplify to? A to the 5/3, very good. So this will be phi over N times A to the 5/3 divided by P to the 2/3 times the bottom slope to the 1/2 power. And let's go ahead and write out A and P in terms of our dimensions of the channel. So A again is equal to B times H. This is going to be raised to the 5/3 power. P is going to be B plus 2H, again, all raised to the 2/3 power. And this is going to be multiplied by the bottom slope of the channel. And we could substitute in numeric values here. So we have 100 is equal to 1.49 divided by 0.015 times 8 times H to the 5/3 divided by 8 plus 2H to the 2/3 times the square root of 0.0004. But as you can see here, we're not going to be able to solve this problem by hand. So we're not going to be able to isolate H on one side. So this is going to have to be solved iteratively. So let's go ahead and do that. I'm going to break out Excel. Okay, so this is a little bit more complicated, but not dissimilar from what we've been looking at so far. So I have an Excel sheet here. So first, let me specify all of the parameters that we have for this problem. So we have our roughness. This is given by 0.015. We have our coefficient phi. This is given by 1.49. We have our bottom slope. This is given by 0.0004. We have our discharge, which is known. This is given by 100 cubic feet per second. We have our bottom width, which is given by 8 feet. And we have, well, we have H, which is our unknown. So I'm going to give this an initial guess of 6 feet. So we have to iteratively solve Manning's equation to determine the value of H that meets this given discharge of 100 cubic feet per second. So what I'm going to do is I'm going to create 2 helper cells to compute the area in the wetted perimeter. So first, I'm going to specify a cell for the cross-sectional area. This is going to be equal to B, the bottom width, times H, the depth of water. Next, I'm going to create a cell for the wetted perimeter. So this will be equal to B plus 2 times H. This should end up with an area of 48, a wetted perimeter of 20 for this initial guess. And finally, we have to create an objective function, just like we've been doing up to this point. So our objective function is going to minimize the difference between the known discharge and our computed discharge as given by Manning's equation. So let's go ahead and do that. So our objective function, so first I'm going to compute the discharge using Manning's equation. So that's going to be phi divided by n times the cross-sectional area to the 5/3 power. So note how I'm putting that 5/3 in brackets here. Don't forget to do that. Otherwise, it's going to evaluate it as B8 to the 5 divided by 3. We are going to divide by the wetted perimeter to the 2/3 power. And we're going to multiply by the square root of the bottom slope. Is our objective function finished? No. So what else do I need to put in here? Okay, we're going to subtract the known value of Q and we're going to try to minimize that difference. So I'll go ahead and paste this to the side, but I'm just taking Manning's equation, computing the discharge, and then subtracting the known discharge. So we can solve this either using solver or goal seek. I'm going to go ahead and use goal seek just because it's a little faster. So I'll go to what if analysis, goal seek. I'm going to set cell B10 to value of 0 by changing cell H. And if I hit enter, it will find the value of H that satisfies that objective function, which is about 3.97. So we can write that answer down. Let me go ahead and write it down in our notes. So using solver or goal seek, we get an answer of H is equal to about 3.97 feet. Okay, there's a special name for this depth. So this is something you're going to want to know. So the depth at which uniform flow occurs is called the normal depth. This is just a piece of terminology that's used within open channel flow hydraulics. So normal depth, this is the depth at which uniform flow occurs. Okay, are there any questions on this example? I'm going to go ahead and put up the Excel sheet again, just so you can see. Any questions conceptually on how I solved this problem? Yes. Yeah. So let's go ahead and change back our depth value H. So what I did was I went to what if analysis, goal seek. I'm going to set cell B10 containing our objective function to value of 0. I want this cell to go to 0 by changing cell B7, which corresponds to our depth. So when I do that and hit OK, it gives us a depth of 3.97 feet. You can solve this either using solver or goal seek. It doesn't really matter which one you choose. All right, so with that, for the rest of the class, I have an example for you to work on. So this is under Canvas quizzes, in-class uniform flow problem. It's going to be similar to the example I showed you, but with a more complex hydraulic geometry. So we're going to be looking at a trapezoidal channel. So go ahead and work with small groups to solve this problem. You should be able to do it by the end of class, but if not, this is due on Friday. All right, any questions before you get started? Nope, okay. Good luck.